Hey guys, so for the few of you who are the unlucky contestants of a quick quarantine here, just wanted you to be able to keep up with class. So on Monday and Tuesday, predominantly, we're just working our way through some Chapter 1 information. You have the PowerPoint at your disposal. So I'm going to talk you through what you're there. I'm going to be telling you through what the add-ons are that I would be saying in class, try to show you a thing or two so that you can feel like you are right here with us, even though you can't be. So give me a second to share my screen with you. Okay. All right. And if I take you guys to our PowerPoint, the theme of the day, all right, for Monday is introductory to chemistry. All last week we spent talking about lab safety. All right, so we can take you into the lab this week if you do happen to be back with us. All right, but the first few classes are all about just an introduction to chem and the types of chem and some of the definitional beginning of the year type things related to chemistry. All right, so I would be remiss if we didn't talk about, what chemistry is, definition. If you look it up, it says it's going to be the study of matter and how we can changes that it can undergo. It's a physical science, right? Chemistry can be focused on the human body, which would make it biological science and biochemistry. But predominantly, we're talking about doing reactions and doing manipulations that are just happening around us, not within us. And with that in mind, we get two major categories. We can change something physically, which you'll learn is called a physical change, and we can change it chemically. We can alter fundamentally what is it at its deep down parts. Right. So there's lots of versions of chemistry. We tend to focus on 5 of those here in class. You get organic, inorganic, physical chem, analytical, and as I mentioned before, biochemistry. Each one of them is analyzing something a little bit different or focusing on something a little bit different. And I wanted you to have an idea of what are some careers that you could see in each of these fields. So the first one, which we don't do very much of in here, is called organic chemistry. The organic chemists focus on fundamentally the element carbon and the fact that it can make big, long chains like you see here at the top of this slide. All right, those big, long chains string together and they have lots of different characteristics, but there's so many organic compounds out there, it gets its own branch of chemistry dedicated to it, even though fundamentally it only focuses on one of the roughly 120 elements that we know of on the planet. The one you guys will see in here a lot is inorganic. All right. So even though you have some organic careers about like developing food and working with plastics and pharmaceutical drugs and things like that, we in here tend to focus on inorganic, the other elements from the periodic table. So what are some things that we will see as we work through? Well, we'll focus on things that we pull from the earth, like mining and metallurgy, things like ceramics. We can gather up samples from the soil outside and see what's in it. We can look at crystals and things of that nature, and we can look at how they affect our environment. So we'll do a lot of that. We'll look at a little bit of food and food content and water and things like how much calcium can be in your water, things of that nature, and how we can change one substance into another if we burn it, for instance. Physical chem focuses on both branches, organic and inorganic, but it is entirely focused on energy. All right. It wants to know what type of energy release or consumption will I get out of, say, a chemical reaction? How will the energy affect what's going on in a chemical reaction? These tend to be the ones you guys always like to ask me about is, Mr. V, will this thing explode? If I did the physical chem end of things and calculated the energy release, I could tell you, would it explode or would it just make a banging sound? Would it release light? Would it release heat? What would it do? So explosives and fireworks, all the stuff with oil and gas that's going around, right? Like Marcellus Shale and energy production. Those are my physical chemists. Right? Analytical chemists, they revolve around identifying unknowns. Right? So anytime I find something and I want to know what it is, whether it be a component from my blood or something from the ground, is this a good place to dig for gold or something like that? An analytical chemist is the one that would utilize things that lets us decide that. They're the ones that would be testing FDA drugs to see if it is good, to let the human body take that in. Your forensic scientists, your people who are at crime scenes, these are analytical chemists as they go through. And as I mentioned before, you have your biochemists, right? And your biochemists, they are going to study the chemistry within inside your body. So just like anything, it's never one thing all at the same time. Obviously, there's overlaps between them, right? But those fundamentally are the 5 things we will focus on when we talk about our branches of chem. Like any lab-based class, mine, Mrs. Sherry's in biology, or Mr. Dro's in Science 8, always has incorporation of the scientific method. If we are going to do experimentation, we need to have a good understanding of the scientific method, right? And the scientific method is how we observe, gather data, analyze it, and then communicate it to achieve some goal, whether it's solving a problem or create a greater understanding of something we already know is happening. Right? Now, technically, they want to think that there may be steps to the scientific method, but that makes it sound like you can make a mistake along the way. I like to think of it more as a diagram. And if I show you what I mean by that, you can see it's more of a circular type thing. Right? No matter what you're doing in any experiment, the moment you start doing things, whether it's in the chem lab or you're watching a football game, right, you are constantly taking in scientific data and your brain is processing it. Sometimes, right, it's very chemistry related. I take you to the back, right, and I have you mix chemicals and you're observing it and things like that. Sometimes, like I said, you go to the musical and you're watching a show and you're making observations. And there are 2 fundamental types of observation you make. One that have numbers and ones that don't. Right? They always make them sound sort of similar. Right? So I'm going to tell you my trick for remembering the difference. Qualitative data looks like the word quality. And when I think of quality, I'm not thinking about counting anything. I'm thinking about how good it is. Right? Quantitative data looks like the word quantity. And if I ask you about quantities, it instantly makes me think of numbers. So if we are talking about quantitative data, I'm talking about number data. How many yards did the running back run for? Right? How many catches did the receiver have? Right? How many songs were performed in the musical? That's quantitative data. Qualitative data is that non-number data, right? Oh, that was a great catch, where it was looking at the athleticism of it, right? Oh, that song sounded beautiful. That's a qualitative observation, right? I really liked the costumes. That's a qualitative piece of data. And sometimes you get both, right? If you're looking at me right now, I could say I'm wearing one shirt. I'm wearing one tie. Quantitative. I could say my tie is red and black. Qualitative. But if I said my one tie is red and black, you're getting both of those. All right, so as soon as you start making these observations, you develop a hypothesis, which is your proposed answer to a question, whether it's something I prompt you with or whether it's something that you are just coming to organically. Hey, I watched that guy run for a lot of yards in the football game. I'm wondering if he's a pretty good athlete, or Mr. V said we were supposed to measure how much of this substance got produced. And based on what I'm seeing, these numbers, I'm thinking it went well. All right. So your hypothesis is simply your answer to a proposed question. When I set up the lab, I tend to propose the question to you because I want you to learn something. Right? But any hypothesis, right, is meaningless unless we move on to test it with an experiment. Right? When I look at a tall person, I think, wow, I bet they're good at basketball. But this is why we have tryouts. We need to test it to see, does our hypothesis hold water? When I look at, right, a substance that's bubbling like crazy, I may see, wow, that thing is definitely making a lot of gas. Well, we need to do an experiment to confirm, well, how much gas is it making and does it support what I thought? For instance, if we went back to our tryout with the tall person who I think is going to be good at basketball, right? We would set up a test, right? Our experiment. I'm going to have them dribble. I'm going to have them shoot. I'm going to have them jump and rebound and do these things, right? And that gets us a lot of data, right? We have data that we are now able to look at. So we need to analyze that data. They made 9 of 10 layups. They made 7 of 8 good passes. They got 8 of 10 rebounds, something like that. And we conclude. And one of two things is going to happen. When we get our data, it's either going to support our hypothesis. Wow, those numbers I threw out sounded pretty good. I bet he is a good basketball player. But the tryout was just one day. And if it's only one day, how do I know he just didn't have a good day? I'm going to make him do it again. I'm going to make him do it again and again and again, every day at practice till I am certain he's good at basketball and now he's on my team. On the other hand, that person walks in the gym. They're tall. Boy, it really didn't pan out. They're uncoordinated. They can't shoot. They only made 1 of 10 shots. Oh, they can't dribble. They keep knocking the ball out of bounds. Right? Oh, they can't rebound. Even though they're really tall, little guys like Mr. V are jumping up and taking the ball off of them. Even though I thought they were a good basketball player, my data doesn't support that. Does that mean my experiment's wrong? Does that mean everything's wrong? No. It just means my hypothesis isn't right. So what do? I go up and I revise it. Hey, that person probably isn't good at basketball, and now my data agrees with my hypothesis. So maybe I have them try out a couple times to make sure they didn't have a bad day to confirm. And then after a while, after many, many, many times of performing the experiment and getting more and more and more data over and over again, you get to develop a theory. And a theory is an idea that explains facts that we have seen. Theories can never be proven definitively. We just have more and more data that asserts those. So on the bottom of this slide, to try to keep that clear, I always have kids put 2 things down. All right, so the first bullet point I would want you to write, all right, is laws explain what will happen. When we develop laws, which isn't here, but I'm telling you we will, laws explain what will happen. Right? Bullet point number 2, theories explain why things happen. So when we things. So the law of gravity tells me what will happen. It says, if I toss this ball up in the air, what will happen? It comes back down. Every single time I toss it up in the air, it comes back down. Every single time. It has been proven that that will happen, right? Over 2,000 years of recording data, we know that's what will happen. A theory explains why. All right, and there's a theory of gravity. All right, the theory of gravity and relativity is that smaller objects go toward bigger objects. So the reason this ball comes down and doesn't float up and away is because it is very, very tiny compared to what we're standing on, which is the earth. So when I throw this ball up, it comes back down because it is attempting to get to the center of the earth. That's the theory of gravity. All right. And we have a lot of experience that makes me think that's right. All right. Until we didn't. Once upon a time, there was a theory that the earth was the center of the entire universe. It was called the geocentric model of the earth. All right. Until one day, this crazy guy named Copernicus came out And he said, I'm not so sure. Looking through my telescope, the way I'm watching other things move, celestial bodies like planets move, it seems like they're moving around something else that's not the Earth, right? And I think it might be around this sun, this heliocentric model. And he was torn apart for it at first until finally the telescopes got better and better and better to the point that he was able to convince people that he thinks that's right. And that's our current theory, that we have a heliocentric solar system as we go. All right, so these are some things that we'll do on a much smaller scale in chem, but that we need to make sure we have some sort of a grasp on. All right, so we are going to set up to go into classes and phases of matter, all right, as we go through. All right, but that would be a great place to stop here. All right, and the rest of that class where you're working on, you guys should be jumping into the section review, which you can find in the Google Classroom. And a lot of the answers to those are in these packets. So you guys can be chipping away at that. So I hope everything's going well at home. I look forward to getting you guys back sooner than later. All right, and I will see you guys soon.